Pre-calculus, what's poppin'? This is Mr. Taryn here, and we are going to take a look at 2.1 part 1, which is being able to graph, analyze, and determine key features of a power or radical function. So let's get rolling here. Our objectives today are just to graph and analyze power functions and actually radical functions as well. Functions, we're going to continue to move on here. Just some basic vocabulary here. A monomial function is just a function with only one term. So something like maybe 4x to the fifth. Even though we have a exponent here and a coefficient, this is still just one term. So that would be an example of a monomial function. A power function is a type of monomial function that can be written in that form. Don't worry too much about that. With the vocab and stuff, you can read that on your own. A radical function is just a function that is written with this square root sign, or if you remember, you can convert back and forth between radical form and rational exponent form. Either way. We're going to move on here. Here's just a quick slide that shows you kind of all the key features of the different types of functions. So notice these are all monomial functions. If we have a positive exponent and our exponent is even, it will have these sort of characteristics. If your exponent is even but negative, it'll have these characteristics. If your exponent is odd and positive, it'll look like this over here, and so on and so forth. You can try to memorize these. I wouldn't. To me, the easiest thing to do and the best way to truly understand what's going on is just to graph the function and then come up with all this stuff on your own. So that's what we're going to do. Let's take a look at this example. We have the function f of x equals 1/2 x to the 6th. What I would do with this question is the first thing is I would punch this into your graphing calculator and graph it. If you were to do that, you will get a graph that looks more or less something like that. Okay, so that's what the graph looks like. It doesn't have to be perfect, but on assessments, try and include at least a few points. So let's start here. We're gonna start answering these questions. So the first thing I want to do is find the domain. So I'm going to use a D. So domain are all the x values that exist. If you look at the graph, it looks like it's going forever this direction and it's going forever this direction. It's going both forever vertically upward, and it's going both this way and this way. It's going forever to the left, it's going forever to the right, and it's going forever up. So that tells us a lot of things about it. First and foremost, our domain, since it's going forever to the left and forever to the right, there's no discontinuity there. I can just simply say the domain is going to be from negative infinity to infinity. Let's take a look at the range, and we'll switch colors here. The range is only the y values. So if you look at my graph, my y values start here and go up forever, or here and go up forever. So it looks like my range values are going to be 0 to infinity. Now be careful. This graph is actually touching, so make sure you're using a square bracket. Let's take a look at intercepts. X-intercept, y-intercept. If you notice the graph, both those happen right here at the origin. So my x-intercept would be 0, 0, and my y-intercept is going to be 0, 0. Next, we're going to look at end behavior. So for end behavior, you really want to look at the very ends of your graph. So notice your graph is going this way forever. That means it's going to the left forever. So we could say something like the limit of f of x as x approaches negative infinity. Now pay attention to the way it's written down. You've already done continuity, so you should be used to these limit statements. But the limit of f of x as x approaches negative infinity, so as x approaches negative infinity, our y value, our f of x value, is approaching positive infinity. For the other side, limit f of x as x approaches positive infinity. So we're going to ask ourselves, as my x values are approaching positive infinity, what's happening to my y values? Well, my y values look like they're going up to positive infinity as well. When we're looking at continuity, if you notice, this entire graph is going the whole way. There's no jump discontinuity, there's no asymptotes. So this function would be continuous. And sorry, I'm running out of room. So that's continuity, and then increasing and decreasing. If you look, we're going to go to the highlighter here. If you look, whenever you're looking for increasing and decreasing, you always want to read your graph left to right. Okay, I cannot stress that enough. Read your graph left to right, just as you would a book. So if we look at our graph going left to right, starting here, the graph is going down all the way until it gets to here. Now, a lot of people see these arrows up here and think, oh, okay, well, it's going up. No, it's actually, when we read it left to right, it's moving down. So we could say that the function is decreasing from the interval of negative infinity to 0, which is right here, and then it's increasing from 0 to positive infinity. And so that would be how you solve this problem. Let's take the answer. That looks more or less like something we have. All our answers are good, so we're good to move on to the next example. In this example, we have a function with a negative exponent. It's no big deal, really. Just go ahead and graph it in your graphing calculator just like you normally would. You can either leave it like this, or you can enter it like this. And you should get a graph that looks something like what's shown. So once you have it graphed, now we're going to take a look at all the important stuff to it. So the first thing we're going to look at, again, is domain. When we look at this graph, the function looks like it's going all the way from over here, all the way, has x values that exist all the way to here, but it looks like when we get to an x value of 0 here, there is no y value, or it's undefined. You can also see that right here. Okay, so our domain would be from negative infinity to 0, and then again from 0 to infinity, which is this other side. Okay. The next thing we need to look at here is range. When we look at the range here, again, if you look at this table here, your f of x values get really, really, really close to 0, but never actually touch. So our range looks like, remember, range is vertical, looks like it's going from 0 with a parentheses, because zeros is not included, and this graph goes all the way up to positive infinity. So there's your range. Let's erase some of this stuff again, and let's do another one. We need to find intercepts. So I'm going to go x-intercept, y-intercept, and let's ask ourselves, does this line actually touch the x-axis? It does not. So all you can do is just write none. How about my y-intercept? Does the graph ever touch the y-axis? It does not. So you would just write none. Let's take a look at end behavior. I'm just going to write end. Remember, when we're looking at end behavior, we're looking at the outsides of the function. So if you look at this function, as it goes further and further left, what's happening to your y value? Well, it looks like it's approaching 0, but it's never actually going to touch 0. So remember our the way we write this with limit statements and all that, we're going to write the limit of f of x as x approaches negative infinity would be 0. The limit of f of x as x approaches positive infinity, when we take a look at our graph, it looks like when we go to the right, the graph is also approaching 0. So that takes care of end behavior. Let's look at continuity here. We can clearly see both from this table and from the graph that we have infinite discontinuity at x equals 0. And then finally, where the function is increasing and decreasing, remember when you're doing this, you always have to read your graph left to right. So it looks like my function is increasing from negative infinity way out here, all the way, it's increasing all the way till we get to 0. And then it looks like it's decreasing all the way, or sorry, from 0 to positive infinity. That should take care of everything. I'm not going to go through every single example on it, but I just want to give you a quick short video on how to graph or how to analyze and find key features of these graphs. The rest you can do on your own. I will provide this as well. And good luck.